Everybody's turned in? Get my... All right, so how about that first one? We're going to do U substitution on both of these, right? And on the first one, what is the U that you're going to use? X cubed plus 1? So if you make ux cubed plus 1, the derivative of that with respect to x is 3x squared. So you could rewrite this as du equals 3x squared dx. Right? And you have x squared dx here. You're trying to see if you've got that over here. If I rearrange this, then you have it right there. So we just need to get rid of that 3, so we scale both sides by a third. And then I rewrite the entire problem. So the problem becomes integral cosine of what? U times this, which is 1/3 du. And what can I do with the 1/3? Take it out. So 1/3 integral cosine u du, antiderivative of cosine of u. So just sine u plus a constant. And then replace u with 1/3, x cubed plus 1. So there we go. Do what? Are you talking to yourself?
We're just discussing.
Forgot plus c? Okay. Questions?
Yeah, I think we forgot this.
So there are some professors out there that will count it completely wrong if you forget c. I won't count it completely wrong, but I won't give you full credit if you forget c. All right, so that's that one. Any questions on this? All right, the next one was sine x over 1 plus cosine squared x, right? So use cosine x. The derivative of that is negative sine x, right? And then I have that over here. What I actually have is 1 over 1 plus, you could write that cosine x squared as cosine x squared. That's what that means, right? Then times sine x dx. So this sine x dx is here. I'm off by -1, right? So negative du equals sine x dx. And I think I can rewrite the whole problem now. So this becomes integral 1 over 1 plus, this is u, so u squared, times negative du. Pull the negative out of the whole integral, negative du. The antiderivative of 1 over 1 plus u squared is arctangent, but I have a negative out there. So negative arctangent of u plus c, which is negative arctangent of u, but u was cosine x plus c. That's it. What do y'all think? No?
Slow down. Get the English, man.
Show of hands. How many of you got the first one right? First one? Most of it? How many of you got the second one right? Not as
Get out of
many?
here with that.
Okay.
Hey, hello.
Any questions over homework? Do you have it right there with you? Which one?
I was just, it's to the bottom.
15.
I was just confused. Oh, yeah, I was gonna put that one too.
There you go. If your notebook smells like skunk now, I apologize. I just can't get it off my hands. Okay, so what is the variable that we are, what is the variable in the problem? X, because dx, that indicates the variable. Now, a and b we're going to assume to be constants. Right? Just any number, but it's fixed and we don't know what it is. So I heard something for you. What was it? 3ax plus bx cubed. Let's just see what the derivative of that would be. So what's the derivative of 3ax? Just 3a? Are we comfortable with that? Yes? Derivative of this? So the 3 comes down. The b is just going to come for the ride, so 3b x squared dx. That's what we've got, right? Since there are two terms separated by addition or subtraction here, I put parentheses around there. Now, do we have that up here? Kind of, right? Kind of. I'm off by 3. So if I divide both sides by 3 here, or if you'd like, factor 3 out, then divide by 3, you're going to get a plus bx squared dx, which matches up exactly with all of this, right? So that whole part right there that I circled is actually going to be 1/3 du. And what's underneath the root, right, the radicand, is going to be my u. So how do you want me to write this? You want the 1/3 du? How about I do it this way? 1/3 du, right? And then, since all this stuff has already been accounted for, I need this on the bottom, so square root on the bottom. So I just better put a 1 up there, right? And then just u, root u. And at this point, this is like one of the first things we learned with integration, which is the power rule. So we're just going to rewrite u as a power of u. Right? This is equivalent to 1 over integral u to the negative 1/2 du. And then just use your power rule. So I'm going to add 1 to this. When I add 1 to that, I get a 1/2. So out front, I'm going to have the 1/3 that's coming along. I have 1 over 1/2, which flips and becomes 2. And I have u to the positive 1/2, and then plus some constant. 2/3 instead of 1/3 times 2, so 2/3. This is really the square root. So I'm going to go square root of u, but u was 3ax plus bx cubed plus c, and I'm done. Did that clarify everything for you? Okay. Was the trouble with the a and the b, like kind of like what are
I
those?
just didn't know what to make the U. I just didn't see it.
Okay. Okay. Which one? Can you read it to me? Sine hyperbolic squared x. That. Any thoughts on it? Sine hyperbolic. Sine hyperbolic x, right? For you? The derivative of that. What's that? You did? Oh, you did the whole thing? Yeah, the derivative of this will be cosine hyperbolic x dx. And then that's pretty straightforward for the substitution. Do you see it? Integral sine hyperbolic squared is going to become u squared. Cosine hyperbolic x dx is exactly du. That's 1/3 u cubed plus c. And then just replace u with sine hyperbolic. So how do you all feel about the substitution? The u substitution? Feel like when you left class you felt one way last time. Now you're coming back. Do you feel like you've gained some confidence in it with doing your homework? If you did your homework, you should have gained some confidence, hopefully. If you didn't do your homework, well, remember what all those other students were telling you? Good luck. Do another one? Which one?
That'd be a sine pi t dt.
Sine of pi t dt, that's it?
Yeah.
Okay. So there's two ways to approach this. Last class I was telling you that if you're integrating a function with a linear expression in it, do you remember this?
Yeah.
That it's the antiderivative of that function evaluated at the linear expression plus c, but you have to scale by 1 over a.
So we just do 1 over pi?
So you're going to have 1 over pi, because pi is like this is like ax.
Yeah.
Okay, that's exactly what it is. And then the antiderivative of sine, which is negative cosine. So make this negative 1 over pi, cosine of what though? Pi t plus c. That's the quick way to do it. And that's the way I prefer you kind of have
I just do the whole thing, so I'm too scared.
the way that you approach it. Now, if you didn't do it that way, then you would do this u substitution. U is pi t. And then you go du is pi dt. So you're going to replace this with u. Replace dt, well, you don't have much to work with. You just have this, so you multiply both sides by 1 over pi.
Yeah.
And then from here, you would get it. Got it? But if you have to do that on every single one of these later, it's going to take forever. Yeah. Any others? All right, so we'll move on. We are picking up 6.1. So this technique, integration by parts, is our next method, okay? So right now, here's what we have. We have power rule, right? We have, do we recognize it from Cal 1 as something, the derivative of something from Cal 1? So recognition, right? Those will kind of group together, okay? That's our basic techniques. We have u substitution, which is what last class and homework from last class was about, right? And what the quiz was about. Now we have a new method called integration by parts. And this is a formula that we use. Problem with it is that it's not a formula that works every single time with every integral. It's only when we have a certain thing happening within the integrand. All right, so I'm going to show you where the formula comes from first, then we're going to practice using the formula. All right? So I have up in the notes that if you were to sit here and call some function of x u, now usually we wrote this in like college algebra, we said y is f of x, right? Because y, we could graph it, but we could have called it anything, right? Let's call it u. And v is g of x. Then if we wanted to take the derivative of the product of these two, so if you say what's u times v, what's the derivative? You would use the product rule, wouldn't you? So you'd say derivative of the first one times the second one plus derivative of the second one times the first one. Yeah? That's the product rule from Cal 1. All right. Now this is where things get interesting. What I'm going to do now, and by the way, I'll mention to you, both of these are functions of x, right? So the derivative of u should be the derivative of this, which would be a function of x. And v by itself is a function of x. The derivative of v should be a function of x. And u by itself should be a function of x. So everything here is a function of x, isn't it? Okay. So what we'll do now is we're going to take that equation right there, because this is an equation, isn't it? This must equal this. What we're going to do is we're going to integrate it. We're going to integrate both sides of the equation. And I want you to pay attention to what happens here. What happens if you take something, right, and you take its derivative, and then you take its antiderivative? What do you think would happen? Right back where you started, right? You should just get u times v. So like differentiation, and then come through and undo differentiation, you should be back at u times v. So this is just u times v. Now this side, if I'm going to integrate it, I have to integrate the whole thing, right? But I have addition between the two. So I'm allowed to break this integral into two separate integrals. Like this, right? That's just using property of integration that if you have addition or subtraction, you can do them individually. Questions on that? All right, so the next thing I'm going to do is I'm going to take this right here and move this whole integral to the other side. So subtract the whole integral on both sides and leave this integral here. Right? This is just like using equality. You can always subtract something from both sides or add something from both sides. So if I move this one over, subtract this integral over here, subtract it over here, you get u times v minus the integral of u prime v equals the integral of v prime u. Any questions on that? It's algebraic. No? Don't know what I did? Yes? Yeah? Just moving it around. That's it. Just moving it around. Right? If you have something that's positive on one side, you move it to the other side of the equation, it becomes negative. So that's all I did. All right, now what I'm going to do is I'm just going to kind of rewrite this, rearrange it a little bit. Anytime we have equality, right, we can always just write it the other way around. Right? If I say x is 4, I can also say 4 is x, right? So it doesn't matter. I'm just going to write this backwards now. So I'm going to write the integral, and watch this. I'm going to write u times v prime equals, and then this side over here, u times v minus integral v times u prime. So all I did here is I wrote this, but I switched it because it's multiplication. I'm allowed to do that, right? And then this side over here is the same, except here it was multiplication, so I wrote it that way. Okay? We're almost there. The only thing I did here was a slight change in notation. Instead of writing v prime, which meant the derivative of v, right? That meant the derivative of v. I'm going to write dv, which also means the derivative of v, right? And over here, instead of writing u prime, I'm writing du. So nothing has changed, just the way I'm writing it, notation-wise. Okay, this right here is the integration by parts formula. This is it. Yep, that's what we're going to call it in just a second. But let's get our heads around what's happening here. All right? What I'd like to do now, this is the one that we're going to memorize. All right? But let me just write it in different terms. This really means u was a function of x, wasn't it? So that was some function of x, f of x, times the derivative of v. Now remember what I had wrote up here. U was f of x, right? And v was what? G of x? Two completely separate functions, right? They're not the same functions. They're different functions. So f of x is u. Now dv would be what? G prime of x. And now what I'm going to do is I'm going to put dx because I can indicate the variable within here. Equals u times v. That's just these two multiplied, right? F of x times g of x. And then minus the integral of v, what's v? G of x. And what's du? The derivative of f. And then again, I'll write dx. See, that's kind of a longer formula to remember if you write it out that way. This is the shorter way of doing it. All right, so let's try and understand what the hell this formula tells us, all right? This is the most critical part of today, all right, is you understanding how this formula works. What we have is on the left side is the integral that someone gives you. You walk in, I give you a quiz, I give you this integral right here. And what you do is you look at that integral and you look inside of it, and inside of it when you're looking at it, you recognize two things. You recognize some function of x. I don't know, x squared, sine x, whatever it is, right? And next to it, you see some other function of x that has nothing to do with this function. But you recognize that it is the derivative of something. It's like maybe this is cosine, which you realize is the derivative of sine, right? Understand? Or maybe this is x squared, and you realize that's the derivative of 1/3 x cubed. Understand? And then, according to this formula, you can rewrite this integral as this new problem where this part has no integration in it at all, and you create a new integral. Do you see this is a brand new integral? What is the difference between this integral and this integral?
It flipped.
It flipped. What flipped?
The derivative.
The derivatives switched, didn't they? See, over in the first integral, this function that you identified, in the new integral, it's the derivative of that function. And this function, whatever it was in the new integral, is its antiderivative. Do you see? Yes? Okay. That's the heart of this formula. What it allows you to do is take something complicated, and hopefully this switching of the derivative makes the problem easier. That's what you're hoping for. But it doesn't always work. That's what I said. It has to look a certain way for this to be valuable to us. All right, so the integration by parts formula is what we call a transferring of the derivative. We are transferring the derivative from one function to the other. Now, this formula is the one that I said you need to memorize, and the reason is because there's a little cute saying that you can memorize to help you with the formula, which is right there. And you know what? I forgot to write it in my notes. I meant to write this in my notes, not the v prime. So look at this and then say to yourself, ultraviolet minus VOODOO, voodoo. So ultraviolet, U times V, minus, now there's an integral here, you just have to remember the integrals here, minus the new integral, which is voodoo. Voodoo. Right? Ultraviolet minus voodoo. I didn't make it up, okay? It's not my original thing. I learned the same thing when I was in your shoes, so. Or you just memorize it, okay? However you want to memorize it. Now, you ready to see it in action? Okay, I think I have examples to work through. Yeah. So here are several examples. Each one of these on the side, I put a little note to the side of each of these that gives you a little more information about the type of problem we're doing. So let's look at the first one, part A, which is a basic integration by parts. This is about as simple as it's ever going to get when it comes to using the integration by parts formula. We have x times sine 10x dx. Now let's first appreciate the fact that there's nothing we can do walking in today with this integral. We cannot split this into two integrals, right? because it's multiplication? Can't just give me the antiderivative of this and this one separately? Basic U substitution. Do you see something in its derivative? 10x? What's the derivative of 10x? 10, but you have an x out here. Maybe there's a way it could work, but if you go and mess with it, it's not going to happen. So for u, for like a basic substitution, if you let u be sine x, the derivative of it is cosine x, right? Which doesn't appear anywhere up here. So do you all see that right now, a basic u substitution, no go? Yeah? Trying to see, make sure my microphone's working. Okay. No go with basic? So maybe we can use integration by parts. So what we need to do is we need to use the formula which says that is this on your formula sheet? Yeah, I think it is. Hold on, let me see. It's formula number 1. You see it? So what I'm going to do is I'm going to look up here within this function, or within this integral, and I'm going to see, is there something that I could call u, and is there something that I could call the derivative of some function, which I'll call dv. And what I want is that whatever I choose for u over here, its derivative is going to appear over here. And whatever I choose for dv over here, its antiderivative is going to appear over here. Understand? So you have kind of two choices here, don't you? Does everyone see clearly that there are two functions being multiplied? We have x, and you have sine of x, or sine of 10x, right? That's kind of our two choices. Now let's look at both possibilities here. If we let this be our u, then this would have to be the dv, right? And whatever you choose to be dv, you must bring the dx with it, okay? So that's one choice, right? That's one way I could do this. But let's analyze mentally what would happen in the new integral. In the new integral, we would have v, which means you would need the antiderivative of just this, right? Can you tell me the antiderivative of just this? You just asked about that, right? Sine pi t just a second ago? This is the same problem as that, except sine 10x, right? So you could do this, right? Negative 1/10 cosine 10x, right? That's what. So you're comfortable with putting the antiderivative of that here, aren't you? Okay? And then whatever we choose for the u, in this case would be the x, over here it would become what? 1. Ooh, that's nice, right? Because if it's a 1, then really the only thing that would be left there would be what? The antiderivative of that. So I would have a cosine function over here, but I would no longer have this x out in the front. Do you see that good thing? Now, what is another option? Switch it. So this is option 1, which I like. Option 2 would be I would do something like this. I would choose this to be the u, and this, along with the dx, to be the dv. Understand? Let's talk about what this would be in the new integral. In the new integral, I would need to have v, which would be the antiderivative of this, right? What's the antiderivative of that going to be? 1/2 x squared. So in this new integral, I think I'll actually write down this integral right here. This new integral would have the antiderivative of this in here, 1/2 x squared. And then times what? U would become what over here? Right? This u is going to become du. So the derivative of that, do we know the derivative of that? Yes, it's 10 cosine 10x, right? That's antiderivative. Right? And then I'd have dx out here. Is this integral nice? Why not? Why not?
There's too much data.
Yes, but even worse, look, This one was x in front of a trig function, right? This one's now what? X squared in front of a trig function. It's actually become more complicated, hasn't it? Compare that to this one. I did it mentally, but I didn't write it down. This new integral over here, you said we would need v, right? Which is the antiderivative of that. We all said that that would be negative 1/10 cosine 10x, right? That's what we said. And du, which is the derivative of that, which you said was 1, right? So this would be it. Which integral would you rather work with? The first one, right? Because now this is just a trig by itself. No more x out front. See that? So by choosing the u the correct way, we were able to create a new integral that no longer has the x. So we actually kind of killed the x in the new integral, didn't we? And that's the key to integration by parts. You want to make a proper choice for your u and your dv so that in your new integral it's easier to solve. Got it? Now let's go through and work it formally now that we've thought about it. Still going to leave that formula up there. Here's where I do my work. Well, I'll get the formula out of here. It's right up. Well, I took it off the board. I'll put it over here. Integral u dv equals uv minus integral v du. All right, so this is the proper choice. Different people do this different ways. All right, so I always do my integration by parts the same way. I always start with a table. I make a table, and I'm going to fill the table in. The pieces of the table that will be given to me by the problem will be the two pieces of information that I had to identify, which were the v and the dv, right? Those were the ones in the original problem. So in this table, I'm going to put u here, dv here. The things that I'm going to have to figure out on my own is I'm going to have to figure out what v is and du. So the way I want you to think about this table is that this column is for my u stuff. This column is for my v stuff. I am going to plug u in directly from the integral. I'm going to plug dv in from the integral. When I go up in a table, I integrate. When I go down, I differentiate. So once I have u to get to du, I differentiate. When I have dv to get to v, I integrate, go up. Yes? All right, so what did we say our u was going to be? X. And we said our dv was going to be sine 10x dx. Make sure you bring the dx with you, okay? Don't forget the dx. I look at that and I get upset when I see no dx in here. So now, let's do the left side. Let's go down. So we're going to differentiate, right? For differentiate, I'm going to differentiate down. What is the derivative of x? 1, but I need to have the variable with me. So I'm just going to put 1 dx. If I divided both sides by dx, I'd have du dx is 1. And I'm just basically bringing the dx back over. Now up here, going this way, I'm going to integrate, right? So I'm actually integrating this, aren't I? To go back up, to get v. And you just told me what that was going to be. Negative 1/10 cosine 10x. Now no dx, because we integrated, right? We integrated, so we would put plus c here, wouldn't we? But I'm going to just, at the very end of my problem, I'm going to throw a plus c. I'm just going to remember plus c at the end all the time. You could bring it here, but it's going to complicate things. All right, you ready? That's it. We filled the table out. Everything from here on out is just plugging in. So this integral becomes, first of all, what? Ultraviolet, u times v, which if you look at your table is the multiplication of these two straight across, isn't it? So multiply x times this, and what would you have? Negative 1/10 x cosine 10x. Okay, good? Ultraviolet. See, no integral here, right? There's no integral in the formula, ultraviolet. Then minus, right? Minus, now an integral of what? v times du. V times du. So now we're looking at multiplying diagonally, here to here. So what's negative 1/10 cosine 10x times dx? Just that dx, right? So it's negative 1/10 cosine 10x dx. I'm running out of room here for my camera, so y'all with me? You see why it was so important to put dx here? Because if you didn't, then when you multiplied, you wouldn't have dx, and then the integral wouldn't be written properly. It would be bad math penmanship. And in the future, this is not going to be 1. It's going to be more complicated later. We good? Okay, so we're not done, right? Like, we haven't actually done that integration. What we've done is we've used the formula to convert an integral that we could not handle into an integral that we can handle. We have transferred the derivative to this, removed the derivative from this. So we have negative 1/10 x cosine 10x. That's this. Now, what do you want to do with this minus, negative, minus? Bring it out as what? Positive 1/10? And I'm still not going to integrate yet. I'm just going to leave this like this. We good? Have not done any integration yet? Just kind of cleaned up the inside? Now, let's find the antiderivative of this. So this is cosine of a linear function. What is the antiderivative of cosine of a linear function? It's going to be sine, right? So here's the 1/10 here, times. So because this has an a in front, right, you have to scale by it. So 1/10 again. Antiderivative of cosine, you said, was sine 10x, right? Plus c. Does anybody have a question on where any of the numbers here came from? Yes? Good. Thank you.
The second 1/10?
Okay. So just this 1/10 is from here, right?
Yeah, we pulled that out.
Yep. That was right there. So the antiderivative of cosine of this, antiderivative of cosine is sine. But remember last class we said that if this is linear, ax, you have to scale by 1 over a? That's it right there. See that? Yes.
What happens if, like, remember you did it the other way in red? If you got that, I guess, sort of problem, do you have to keep doing it like L'Hopital's rule, like over and over again, or how do you go about it?
Part C. You see part C? What we're going to do?
Okay.
Repeated integration by parts. But if you had done it the other way, the red way, you would actually have been going backwards. You would have been making the problem more complicated each step.
Okay.
So it's not one of these things where it's like you pick U, you pick dv, like you make this choice, and you know what, if you get it wrong, it's okay, you'll eventually get there. It's not that. If you make the wrong choice, you could be on an endless journey. But you should hopefully recognize that the problem is getting harder and harder and harder. Each integral is harder and harder. So, yeah. Okay, so the only thing I could do to clean this up a little bit would maybe make this 1/100th. And that's it right there. And then we could check it, right? I'm not going to. But you would have to do what? In this first term, you'd have to do a product rule. You get all that derivative taken care of. You come in with this derivative. You put them all together. You collect. You cancel stuff out. Whatever happens, this is what you're going to be left with. So do you see, we've undone, just by throwing a little x out in front of a trig function like this, it makes the antiderivative a lot more complicated, doesn't it? And that's what we promised, right? I promised this from the beginning. Undoing, right, reversing differentiation is a much more difficult process than differentiation is in Cal 1. Because in Cal 1, right, it's chain rule, product rule, and there's no variation, there's no deviation from those formulas. All right, let's look at the next one. A not so obvious integration by parts. This one's not so obvious. Arc sine pi x dx. So we run through a couple of things first. You know, is this a power? No, you can't use power rule. There's no x to a power. Is it something you recognize? Like, I hope everyone understands, like, you should recognize that you know the derivative of that, right? But not the antiderivative. That's not something you can recognize. Basic U substitution.
If it was just regular sign, then
We'd be done.
for sure.
Yeah, negative 1 over pi cosine pi x. That's right. Yep. So does everyone see we're kind of, everything that we had before today is off the table? So integration by parts? Which means you have to come in here and you have to find some u. You are responsible for identifying a u. You are responsible for identifying the dv. The last problem, we chose our u to be x. We chose our dv to be that cosine thing, right? Or was it sine? I don't know. Whatever. We need two things, right? But if you look at this, this is really just one thing, right? This is not multiplication in here. This is arc sine of pi x, right? This is the argument of that inverse trig function. So this is all one clump of shit. You can't pull this apart, right? This is all one big piece. Which means that the only other thing left is that piece, right? So you only have two choices, right? I mean, there are two things there, I guess is what I'm trying to get at. This right here and the whole thing.
So you can use the function within a function as an argument? Indicating, because then in pi over x, or pi x, isn't that a function within?
Okay, you cannot choose as your u a function that is inside of another function. It has to be separated by multiplication. So the formula is this, right? U times dv, not u inside of v. Now, if that were inside, if we wanted to do it, that's basic substitution. That's what U substitution is, right? You're looking for something that's inside, the derivative is sitting on the outside somewhere. Any ideas?
dv is dx.
dv is dx. Now, let's think about what would happen here. If dv is dx, you would have to integrate to go back up, wouldn't you? And this is like 1, isn't it? So v would be the antiderivative of 1, which would be x. So that would be there, right? So that's doable, isn't it? That's doable. But that forces you to use the other part as u, which would be everything, arc sine pi x. With me? And now you have to differentiate to go down to du. Can you differentiate the arc sine of pi x? Yes. Right? 1 over square root of 1 minus x squared, but in our case, pi x squared. So I'll put pi x squared. Am I done with the derivative?
No. Yeah, it's just pi.
Times the derivative of what's inside, so chain rule, so times pi. And what do I need to slap on the very end of that? Nope, that's integration. dx. I know that's kind of hard to read. I wrote that kind of small, but you'll have that? Any questions? Whew. Okay. Now, just for the sake of showing you, I want to see what other option there was. You have to choose v and u and dv. So another way you could have done it is you could have put dx here, and you could have put arc sine of pi x dx here. Do you see that? Major problems here. First, you have to integrate up. To integrate this up, guess what? That's the original problem. which you can't do to begin with, right? So there's no way you're integrating this thing up. The other thing is, what's the derivative of the derivative? That's going to be like a second derivative, which we never want that happening. So you never want to choose u to be dx, ever. Understand? Another way you can look at it is, if you choose that to be 1 dx, what's the derivative of 1? It would be 0, right? And then it's going to... Look, this is so ridiculous. Watch. I don't think I've ever shown students to this before, but if this is 1, the derivative of 1 is what? 0, and then v right here. Well, I don't know what it is. I have to wave my hands at it. Isn't it this integral? And I'm telling you, like, I have no friggin' idea how to do that. Right? Like, I need to integrate this, but I don't know what that is. Yes? Okay, do the formula. This original integral would be what? U times v. What's u times... Sorry, yeah, u times v. It'd be this times this, right? Minus v du. What's v times du? 0. So guess what you have? That this original integral is? This original integral. Congratulations. Thank you. Blue is equal to blue. I'm happy for you. I mean, you haven't gained anything on that. You see that? You've just kind of confirmed that the original integral you were looking at is the integral you're going to go and try and find. You've gone in a circle. Useless to do it this way. Understand? Okay.
Is that a good way of, if you're working and you're a little unsure, which one should I set up for my table? Is that a nice quick check? Oh, look, it'll zero out. It's going to put me right where I started. Obviously,
You could, well, if you ever are trying to put du to be dx, you know right away you're going to get back to the original integral.
Right.
Okay? The thing that should tip you off is when you choose dv, you better be able to integrate it. If you can't integrate dv, you're in trouble, right? All right, so let's move on here. We're not done. This should turn into ultraviolet, which is going to be this times this. So that's just, I'll put the x in front, x arc sine of pi x. Do we agree? Minus integral voodoo. Ultraviolet, this times this, minus integral of voodoo. This times this. Oh my goodness. This times this, right? Oof. I think I'm running low on room here. I think I'm going to move this. I'm going to move the whole thing over. The original integral is equal to ultraviolet minus integral of voodoo. V times du, which was 1 over the square root of 1 minus pi x, that quantity squared, times pi dx. Everyone see voodoo there? Voodoo, voodoo. And then you look at that and you're like, "Ooh, why did I take this class?" Because I have to. And why did they make you take this class? Because they want to see who can and can't do it. That's right. Trying to weed you out. Sad story is that's the truth. Especially for you biology majors. Engineers need to do well in Cal too. Biology majors usually don't have a vested interest in mathematics the way an engineer would. So this is almost like punishment. It's to thin the herd of doctors, that people who want to be doctors. Engineers just need to, I guess, get to a point where you're thinking this way and you enjoy thinking this way and you like this stuff.
Like wafers.
Yeah, when it all kind of comes together and All right, so now we look at this and you start asking yourself, did you gain any ground? You know, you look at this new integral, look at the original one looked nicer to me than this, right? It was just, what was it? Arc sine pi x? I don't know, maybe not. But there's no more arc sines in here, right? There's no more inverse trig functions. You look at that and you're like, crap. So does anyone see it? Just a basic u sub. This is a basic u sub. Let me do something here. Let me actually square this. So what happens if you square pi x? Pi squared x squared, right? That's what you get. What is the basic u sub that you see? Pi squared x squared is your u. Why would you use that? The derivative of it would be linear, wouldn't it, in x? Because this is x squared, so the derivative of it would be linear. And that's linear, isn't it? But I argue you could go even more.
Minus
1 minus this would be even more, and the derivative of it is the same, isn't it? So do you remember how last class I said you have to be kind of masters of this by the next class? This is why. This is a somewhat basic u substitution problem, but if u substitution is something that you're going to get to next week, then it's very difficult to follow along in here. So at this point, what I'm going to do is make a u substitution. So this is like my new universe is this problem. Okay? This is my new universe right now. I'm just going to work that problem out. So remind me that we need to come back to this and tack this onto the front of the answer. So working with that integral right here, I make a u substitution. U is equal to 1 minus pi squared x squared. The derivative of this will be, you tell me, negative 2 pi, what? Look, pi squared is a constant, isn't it? Negative pi squared is constant. It's just going to come along for the ride, isn't it? Negative pi squared. Derivative of x squared is 2x. So negative 2 pi squared x dx. Now you look back over at this integral right here, and you say, do I have that, or can I match anything up? Well, do you see what you do have over here? Is a pi x dx. So let me just rewrite this over here. Du, see, negative 2 pi times pi x dx. What I did here is I just kind of peeled off one of the pi's so that I could see pi x dx here to match it up with this. See me matching that? So what should I scale by on that over there to make these things match up? Negative 1 over 2 pi du is equal to pi x dx. And that allows me to rewrite the whole problem. What's in red is going to become what?
Du.
Almost like all that du, right? Like negative 1 over 2 pi du. That's what this is going to become. And then I'll have like a 1 over the square root of u. So just this green thing is going to become 1 over the square root of u times negative 1 over 2 pi du. Take the negative 1 over 2 pi, take it out. Change that to u to the negative 1/2, right? And then integrate. Got a question?
Would that become positive?
I'm not even, look, remember I said my universe is here?
Oh.
Okay, I'm serious, my universe is like right here. I'm only living from like here to here. Because my signs are going to get messed up if I try and incorporate all this stuff. So I am not even caring about that negative right now, okay? I will come back and get that. With me? Now, as you move on and get better at this, you can do it all at one time. All right? But I would go slower steps initially. Okay, so what's in this green box becomes negative 1 over 2 pi integral u to the negative 1/2 du. The antiderivative of u to the negative 1/2 is 2u to the positive 1/2. So I'll have negative 1 over 2 pi times 2u to the positive 1/2 plus a constant, right? But I'll throw that in at the very end. Just going to remember. 2's cancel. Negative 1 over pi square root of, what was u? 1 minus all that junk, right? 1 minus pi squared x squared. Plus c. I'm going to bring it at the end. Because this isn't my final answer, right? This is just that green part. Yeah, now I need the ultraviolet minus this, right? So everything, well, I erased the formula, oh well. Everything I had done up to that part was just integral v du. That's what I just finished up. So I need to bring ultraviolet minus in now, in front of that. So you ready for the final answer? The original integral, which was arc sine of pi x dx, is equal to ultraviolet, which was, I don't remember, x times arc sine pi x. Okay, so now I'll do it in a second. Minus now this, right? So another negative 1 over pi square root 1 minus pi squared x squared plus c. And the minus become plus right there. So equals x arc sine pi x plus 1 over pi square root 1 minus pi squared x squared plus c. Of course that's the antiderivative of arc sine pi x. It's obvious. We're done. What do y'all think? You're going to need to practice. I wonder how quickly we could show that this is the derivative. I want to. I want to prove to you it is. I'm going to go fast, though. Product rule here. Derivative first is 1 times the second. Plus derivative of this one, which is 1 over the square root of 1 minus pi squared x squared. That squared, right? Times derivative of what's inside pi times what's out front x. Plus 1 over pi. Now, derivative of the square root of something is 1 over 2 roots of that something. Times derivative of what's inside, which is negative 2 pi x. Derivative square root of something is 1 over itself. 1 over 2 times the root, right? Times derivative of what's inside. Derivative of what's in here is this.
I thought you just need the square of the squared. I thought pi squared was just a constant.
Where? Oh, I'm missing the square. Thank you. Yes. Good. Yes. Okay. Y'all see it? Look. 2's cancel. 1 of the pi's cancel. So all this is negative pi x over the square root of that junk, right? That's what this is. Because see the negative here? That's negative this. Plus over here, what is this one? Pi x over the junk. Square root of junk, right? Positive, take away the same thing. They're gone. What's left? This. So it checks. And it better, yes.
I remember you said that 6 people dropped your class. Was it around this time?
Yeah, right?
I don't know. Maybe it was after the first test. Yeah, I don't know. Look, every one of you can do this, all right? It's a matter of how much are you going to put into it. How much commitment are you going to make to this? I mean, this is not natural thinking here. I mean, it's not natural thinking. It's just, it takes a while to get used to doing this and to get good at it. And as much as I sit here and say you've got to do your homework, and if you watch me and you understand what I'm doing, that doesn't mean anything. I mean that. I mean, it does not matter. If you're following me right here, I mean, it's a good thing you're following me, if you are. But it doesn't mean anything until you can go home and do it. It doesn't mean anything. So I want to encourage you to put in effort that you've never put into a class before, a math class. Didn't I say that? I get a lot of students who are like, man, math has always been easy. This class will test that theory. All right, here we go. Part C, or number C, letter C, whatever the hell it is. I don't even care. C, t cubed. So we're just going to use a different variable, something other than x, just to kind of mix it up. Cosine beta t dt. So beta is a constant. It's like A or B or C. It's a number. We don't know what it is, but it's fixed. It's not going to change. U sub. Now, let's talk about U sub here, because if you did U sub, I think I heard exactly what I wanted to hear. If you do that, what? The derivative of this is t. Here it is. It's trapped in the cosine function. You never want the derivative of your U substitution to be trapped inside something, which in this case it would be. So that's not going to work. It would be nice if this one was squared and that one wasn't, right? Because then you could do a basic U substitution. But you can't.
You can't put du inside of the function. That's what you mean, right?
Can't do what?
Like you couldn't substitute and put du inside.
That's right. You cannot put du. You don't want du trapped in cosine because you can't peel it out on the outside. All right. So the idea behind, let's see how much I can twist your head here. The idea behind the integration by parts is that you split this into two pieces. In the new integral, one of them gets differentiated, the other one gets integrated, right? So if I choose this one to be, this whole thing to be my u, in the new integral it's going to be what?
2t.
2t. And that's nicer than t squared, right? And if I choose this to be the dv, then in the new integral I'm going to integrate it up, right? And it's going to be some sine function. And I can handle that. I'll have to scale it because there's a beta in there. But I can go up with that to sine, right? So my new integral is going to have what two things in it? I mean, basically my new integral is going to have like a t in there and then like a sine and a beta t, right? And there's some constants I have to worry about here, right? Look at that integral right there. Are you going to be able to handle that? How? Nope, U sub, it's not going to work for that. What's the problem? What's wrong with that? Why isn't this one easy? Because the t, right? So why don't we do integration by parts again? Because in the new, if we set up a new integration by parts here and choose this to be my u, what's going to happen in the new integral? It's going to go down, right, to 1, and then when I integrate this one up, it's going to go back to cosine. My new integral, after my second integration by parts, should have a 1 here and then some cosine in there, right? Do you see how I'm thinking through that? So this is going to be a double integration by parts. What you don't want to do is just look at a problem like that and be like, well, I guess I'll just pick one of them to be u and not actually be thinking about where you're headed. That's where you start to get stuck and hit dead ends. And
would that always work with a variable to a power
with
trig function?
absolutely, absolutely, that would. That's a great question. Like if this were like t to the 8th cosine, I would never do that to you. But if it was, we wouldn't, once we're comfortable with integration by parts, we would be like, hey, look, we can do this. It's going to be probably 7 or 8 applications of integration by parts. But I know that every single time I go and do one application of it, I'm going to bring the power down. The next time through, bring the power down. Next time through, bring the power down. And the great thing about it, what's allowing us to do that is when I do this and I integrate it, I get sine. And when I integrate that one again, I get cosine. So this one's just going to keep cycling back and forth between sine and cosine. Now, if this was something that didn't cycle, you'd be in trouble. Because we are depending on the cycling of this in the new integrals to be able to kind of maintain its behavior. All right, well, here we go. This problem is going to be a lot to keep track of. All right, so here we go. I'm going to write it a little smaller since I know where I'm headed with this. Table. Choose a U. Choose a dV. So what did we say we wanted our U to be?
T squared.
T squared. And I'm going to come in here and fill this table in. My dV is going to be everything else that was up there. So cosine beta t dt. I'm also going to mention something else. There are instructors that will teach this topic, integration by parts, where they give you like this kind of cheat sheet sort of idea. Well, some of you have heard of it before. I forget what it's called. But you remember like PEMDAS for order of operations was like this cute way of remembering the way to do things? It's kind of something like that. What is it, Lariat? Okay, so I don't know what it is. Yeah. It's some sort of acronym that kind of tells you if you see an integral and it has a polynomial and a trig function, always let the polynomial be u and the trig function be the dv. So it kind of like guides you. Can you tell I'm kind of being a little sarcastic when I'm saying this? Okay, I don't like that method. Okay, because that's too monkey see, monkey do. Like I have no idea what I need to do, so I'm just going to like follow this, and it's going to tell me do that for u and that for dv. There's no actual thought as to why you're doing it. Does everyone understand why we're letting u be t squared? Because then we can bring its power down, right? To me, it's more valuable. But if you are one of those people who like more of a procedural thing, just go to the tutoring lab and ask them about what, Lariat, or go Google it or something. Lariat for integration by parts, and I'm sure you can find something out there. All right? But I'm going to do it this way. All right, so let's do this. Differentiation down to t dt. And up here, sine beta t, 1 over beta out front. Don't forget that beta in front of the t is like an a, so I've got to scale by it. And now I can go to the formula. This should be ultraviolet, so 1 over beta t squared sine beta t. So that's this times this, minus integral voodoo. So the voodoo is the diagonal, right? This multiplied, which is 1 over beta sine beta t times 2t dt. I just can't believe just how incredibly strong a skunk can smell. I mean, it's amazing that they can produce that. Oh, yeah, my dog got sprayed this morning, sorry. Came in late, you didn't hear the story. My hands smell like skunk.
Have you ever used like Isoniazid for a strong cologne? We use lamicon and skunk oil to make it.
Really?
Yeah, ambergris.
Huh. See, that's what I was thinking. Like, you've got to be able to make a cologne that'll last for 3 weeks if a skunk can do it, you know?
Yeah, dude.
All right. All right, sorry, I shouldn't have distracted you. What would you like to do with this? We're going to do integration by parts again, right? But we have a lot of constants here, don't we? 1 over beta is a constant. 2 is a constant. Let's pull all those out first. See, now this problem, I'm going to keep track of everything. I'm going to do everything in one line. I'm going to keep it going the whole way. So I'm going to rewrite this whole thing. My hand's going to get tired. I'm going to ask myself, why am I in this class again? My hand hurts too much. And so what is going to be out here? I'm going to have minus what?
1 over beta.
Times
Oh, yeah.
2, so 2 over beta. Integral. Now let's rewrite what's still in here, but let's write it in kind of a nicer order. How about we put the t that was still in there in front of the sign? We good? Now I have to integrate this. No questions? I have to integrate this right here. This is now my new universe, okay? Because this is going to require integration by parts to do. So everything, go ahead. I'm going to bring it back at the end, right? Everything from 2 beta on is where my mind lives right now, okay? So in this problem right here, I'm going to make another u substitution, dv over here. What is my u going to be? T. Uh-huh. Who said, Oh. I know that's what you did. We have somebody objects. All right, so we okay with this? T is our u. Everything else is our dv. We integrate up, we differentiate down. That's going to have the effect of killing the t off, right? Which is what we want. du is dt. V is negative 1 over beta cosine beta t. Critically important that we're not making mistakes on our cosine, sine derivatives and antiderivatives now. Because that little mistake, if you made a mistake and said just 1 over beta, that's going to have the effect of turning this into a plus, and then that's going to change the entire problem, isn't it? I mean, the answer. On a test, I wouldn't dock you big time for that, but just beware, yes. All right, so this red part right here, right, this red part is going to become uv minus integral v du, right? So right down here, I'm going to write it. U times v, that's this times this. So negative 1 over beta t cosine beta t. That's these two multiplied. Minus integral voodoo, which is negative 1 over beta cosine beta t times dt. I'm not calling on you. Everyone's, you know, a lot of you are bringing your little name things. I should reward you for that by calling on the people who don't have them. Is this a good thing or a bad thing here? This is a real good thing, right? The t's are finally gone. So I'm going to clean this up again. I'm running out of space. I'll just do it right here. I have negative 1 over beta t cosine beta t. That's this front part. And then minus, so I'm going to bring this out as a plus. 1 over beta integral cosine beta t dt. I don't know if that's coming out on camera, but it's close enough. I said what it is, right? We ready to integrate that? You're going to do just a basic old integration on this, right? This is going to be 1 over beta sine beta t. So I'm at an answer, but I'm not ready to connect it to the beginning part of the problem yet. So I'm at negative 1 over beta t cosine beta t. I had plus 1 over beta, but then I just got another 1 over beta, right? 1 over beta again. When I integrated this, sine beta t plus c, but I'm going to throw it at the very end. I think I'm there. Any questions? Maybe I could go one more line, put those betas together on the bottom over there. 1 over beta t cosine beta t plus 1 over beta squared sine beta t. There we go. That's my red universe right there. That's my final cleaned up version of this red piece right here. Now I'm ready to bring it back and paste it to the beginning part, which is this. And that, yes, that negative 2 over beta that's just sitting there waiting, right? Come on. Just waiting for my answer, right? Must get passed through everything. So if I have two terms, that negative 2 over beta is going to have to pass through everything. So I'll do that. In an effort to save a little bit of time, what I'm going to do is just erase this right there. And I'm going to take this answer and plug it in right here in a set of parentheses. Plus C. Now we're going to clean that up. I'm not going to leave that. I'm going to distribute it through. But we're almost there. So when I pass this negative 2 over beta, it's going to go to here and here, right? Because there's two terms there. So this should be my final answer. 1 over beta t squared sine beta t minus or plus here?
Plus.
Plus 2 over beta squared t cosine beta t. That's when I go here to here. Now here to here minus 2 over beta cubed sine, there's no t, right? Beta t plus c. That's it. And then we could check it, right? We could check it. Yeah.
So if we go all the way,
Just
like,
that squaring. So if we
Yep.
did this whole problem right, it was like you're just like, wow,
But no
this is
C?
flawless. And we forgot the C. Should we be pissed?
No, I mean, I'm not as critical about the C as some people are. I'd be more like just disappointed in you. That's all.
Don't give you full credit, just put a frowny face.
Yeah, a little teardrop coming out of my frowny face. I don't know what's in that thing, but it's got to be better than. All right, so it's 12:30. I don't have enough time to do the next example because it'll take us too long. But look at what it's called, or how I describe it. The rabbit out of a hat, which is, magic, right? Magic, the rabbit out of the hat. That problem seems like it's almost magic the way it works, but it works. And it's a very, very classic problem when it comes to integration by parts. So I'll show you that next time. We'll finish this up. We have all of next class dedicated to integration by parts. I suggest that you do the homework for this. Let's see if it's on here.
is it up to a certain one? So you can all
I definitely did not get everything. Does anyone have a copy of the book with them? I can
Yeah.
run it through. I see one right there. Okay, here, hold on. I got one right here. Thank you. Page 316. It's going to be hard for me to tell just by looking. I should be able to. You should be able to do 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8. Hey, 8 is this one right here. Oh, no, it's not. It's a little different. 9, 10, 11, 12. Okay, you cannot do 13 or 14. So 1 through 12. Skip 13 and 14. Yeah, why don't you focus on doing 1 through 12? just for, because we meet again when? On Thursday. So in 2 days, do those 12 problems. At least you'll have an understanding of what we did today. And we'll come back and...
Page 316.
316, yep. Sorry, I touched your book again. Yeah, we're supposed to have a test next Thursday. Let me get this sign in. Do y'all want to sign this, or you want me to call out names? Sign it on the way out. Just initial. Make sure you have a pencil in your hand. Everyone have a good day. All right, so were there any questions? Did y'all work through those problems? No, I'm going to wait till the weekend. I'm just do it all on the weekend. Okay, you did them? All right. So hopefully you all had an opportunity to practice with those. And there aren't any questions. Well, good. Thank you for being honest.
Would you recommend though, like when you always have a fraction and you do like the new integral sign, just automatically pull it out? That's how
If it's a constant, yeah, you're just going to just keep pulling that thing out. Yeah. Because that just keeps your integrand a lot cleaner. You just got to keep track of all the signs and everything. All right, so we're going to proceed. We have an exam a week from today, right? Your first exam? I believe so. I didn't. I'm a slacker. Well, my daughter was sick. I'm trying to catch a skunk. Oh, actually, I'll tell you what happened. If you really want to know, I'll show you. One of our faculty members sent out this problem. Sometimes we just send each other problems that are just kind of like, hey, look at this. This is kind of interesting. And if you're bored, then do this. And so this was the problem that was sent out, was to solve this absolute value equation. So solve for x, and it's not that hard to do. You can just work through and do. Do you remember how to solve an absolute value? Like absolute value of x equals 4. You set up two equations, x is 4 and x is negative 4. It's the same thing here. Like you have the absolute value of something equals 3. So you first get rid of this outside absolute value, and you say this is equal to 3, and then you do it again, but equal to negative 3. And then you move things around, and then do it again with the next absolute value. And you'll have 2 more to look at, and then 2 more for this. And then each one of those, you do it again, and then you'll have 2 more and 2 more. So it's like 8 different equations or something like that. Anyway, it's pretty easy to solve. You get these are the solutions, right? So it's just an exercise. But then I said, well, what if x can be a complex number? So what if x can be like have an imaginary part to it? So that's a totally different ball game. And I asked that question, and then I went about trying to figure it out. So I spent all of yesterday, and I finally got it about 1 a.m. So that's why I didn't grade your quizzes. I was trying to do a math problem. All right? It was fun. It was real fun. All right. Where do we leave off? D. All right, here we go. So this is the example where I say rabbit out of a hat. And really, yeah, there's nothing like this problem. I mean, this is a very unique problem. You're going to see when we get it done, all right? It's not that it's super hard. It's just something's going to happen that's going to be like, okay, I didn't know we could even do that. First, I want you to notice that when you have the formula for integration by parts, I said the main thing is to remember it's like a transferring of the derivative, right? You're going to look at 2 different things. One of them is going to get differentiated. The other one's going to get integrated, right? And you get to choose. Now, on some of your homework problems, I know we just talked about Nolan, right? What was it, x squared plus 2x or something like that, and then cosine x? and you had to use integration by parts twice. The idea was that the first integration by parts reduces from quadratic to linear, and the second time through it took that linear down to a constant, and that was good. And then integrating this was fine because it just cycled between sine and cosine. So we can kind of hopefully see now by looking at this that this is doable with integration by parts because one gets better as we go. Now look at this one up here. If you look at the e to the 2x, right, if you choose that to be u, that when as you do derivatives, right, what's going to happen? Well, derivative of e to the 2x is itself, and then you'll have a constant in there. You'll have a 2 in there also, but it's not going to like get any nicer, is it? Like this one got nicer? And then when you integrate this one, then it's going to cycle back and forth, right? So are you ready seeing the trouble here? Like, you're never going to get one of these to get better. This is just going to go back and forth between sine and cosine. This one's always just going to be e to the 2x, e to the 2x. So it appears from first glance that this technique will not work on this because nothing's going to get nicer, right? Do you see that? Okay. But it's going to work. So let's see how. So the first thing I'm going to do is set up my table. I'm going to choose a u, and I'm going to choose a dv. And really, you have kind of a coin flip here of how you want to do this. You can choose your u to be the e to the 2x, and then your dv would be the cosine x dx, or you could go the other way. You could let your u be cosine x, and then your dv be the e to the 2x dx, right? Two options, really? So let's go with the first option, which was to let this one be the u, right? And this one's going to be the dv. That's going to be dv, that's going to be u. And let's just see what happens. I thought we'd go around the room today, and I would call on people. And I'd ask them to give me the parts of this, all right? So we'll start right here. And I don't know you real well yet, because I know these guys already. So what was your name? Carmelo. Oh, yeah, that's right. Okay, Carmelo. So if you have your name tag out there, your little name thing, I might... Do you have it? Yeah. Go get it out. Sorry. I was thinking about today, I'm going to have a quiz. Whoever has their name thing gets 100. Anyone who doesn't get a 0. I thought about doing that. You haven't done that yet? I can still do it? You can still do it now. Just get a piece of paper then, Matt. Just so you're fair.
That's our quiz for today.
No, I thought about that. I don't know. I said, you know what, I'll give him one more warning.
You do it later on.
One more warning. Okay, Carmelo, you get to choose. You want to give me DU or V?
I'll give you
Okay, what's V?
the negative sign.
Sine or negative?
Negative sign.
Negative sign?
Or it'll be sign.
Sine? Sine X? Okay. We move on. We'll go with Kirsten.
How did I know you're...
Because you said, I thought you just said call on me a second ago.
What?
No? You were saying, oh, you were saying give you the quiz grade of 100. That's what you wanted.
Yeah.
Oh, but I'll call on you anyway. What's derivative of e to the 2x?
You did it to it?
Okay. And? Times 2? And then what do you always have to put right here?
DX.
dx. Okay, good. All right, so that's our table. Everyone agree? Yep. All right, so now what I'm going to do, let's see, we'll move on. Let's see, Michael? Yeah? I'm going to put this equals, and then do you remember the formula yet, Michael? Like, in terms of u and v, do you remember what the formula is? Okay, so it'll be, so u times v. Perfect. Okay, that's it right there. So I'm going to go u times v. So this times this, e to the 2x times sine x minus the integral of, now let's move on to my back table there. Joel? I'm not going to call on you, Joel, because you have your name tags. So, what do you got? Yes, sir? What's your name? That's right. See, but I have to have visual for it to start to stick. Yeah, I'm going to make you go get a tattoo. What I was going to ask you is what goes in the integral? And you know what? If you're not comfortable with it and you're like, you know what, I don't know, just say I don't know. I mean, it's okay to do that. I was in a Cal 3 class the other day and I had a student. I was like asking him. He's like fumbling around through stuff and like we're all waiting. And I said, it's okay to just say I don't know. That's all right. You don't want to be I don't know when you're taking the test, right?
Yeah.
Okay. It's okay? All right, we'll move on. Yes.
Sine X.
Okay, so you're just going to do this one times this one. So it's V times du. So what would you like for me to do with that 2? Because it's a constant. You want me to pull that out now? Okay. I prefer to pull the constants out. Now that we're in the second day of this, hopefully after homework you've seen. All right, that's where we are, right? And from all appearances, we've done something, but it hasn't really gotten any better, has it? I mean, we went from an integral that had e to the 2x times cosine x dx, and now our new integral is e to the 2x, but now sine x instead of cosine x. So it really hasn't really done much for us, right? Okay. So you might be thinking, all right, well, maybe we should just quit. Let's go and do the same thing. Let's do integration by parts again. Let's use the same u. Let's use e to the 2x again. So I'm going to make a new table over here because there are some things that are slightly different in this new table. So I'm doing a second integration by parts. Do you all see that? So u is going to be e to the 2x. dv, Kyle, what do you got for dv, Kyle? Actually, Kyle, I'm going to call on, what's your name?
Miranda?
Miranda, do you have your name thing?
No.
You don't? Okay, so that's why I'm calling on you. Do you still have it?
Yeah.
You do? Okay, bring it next time, please. All right, Miranda, do you know what we're going to use for dv here?
Sine X.
Sine x. One more piece. Sine x. dx, yes. Anytime you're working with this line, you're going to have dx's on that line, all right? And then, Alexis or Tony, who wants to volunteer? I'm looking for du and v. Okay, so what is it? Same as last time? I'm going to put the 2 in front. Is that all right? Alexis, he made it. He gave you, I guess, the harder part. So v, negative cosine x. There we go. Look at that. We got all the way around the room. Okay, so what we're going to do now is we're going to rewrite the integral, right, using the ultraviolet minus voodoo again. But remember, my entire universe of what I'm looking at right now is this piece, right? So whatever I get with the formula, remember I'm going to have a negative 2 sitting in front of all of it, right? So what I'd like to do is I'd like to rewrite the entire line. I'm going to erase this because I don't have room for it. Can I? Feel okay with it? All right. So my next line is going to read this. Equals e to the 2x sine x minus 2, and then times whatever I get, right? So I'm going to put it all in big brackets. Here we go. All right. Ultraviolet minus voodoo. So what would the ultraviolet be? So it was e to the 2x times negative cosine, right? So I'm going to write it this way. Negative e to the 2x cosine x. Everyone see that? That's ultraviolet from your table. Minus, no? Where the negative? Go back to your table. Right? It was negative cosine here? All right. So minus integral, and then this times the one down here, right? So there's a negative and a 2. I'm going to take that negative 2 out. Right? Maybe I should go a little slower. I'm going to put it in here. Negative 2 e to the 2x, and then what's here? Cosine x dx. Any questions on what I did there? Yes? Sound good? All right, so I'm going to rewrite this. I'm going to put it right here. And you know what? I want you to do this also. On your next line, I want you to write down the original problem, which was this. This is what we were trying to figure out, right? This is what we're trying to figure out. We're saying that that's equal to this right here, which is e to the 2x sine x minus 2 bracket negative e to the 2x cosine x. And then here, when we pull the negative 2 out, it'll become plus 2, right? So we get plus 2 integral e to the 2x cosine x dx. Close the bracket. Any questions? Does anybody see something? The integral we're trying to solve for, right, has appeared again on the other side of the equation. And that might initially seem like a bad thing, but it's actually a great thing, as you're going to see on the next step. So what I'm going to do right now is that negative 2 in the bracket, I'm going to go ahead and pass it through. All right, so let's pass that negative 2 through. I'm going to rewrite the left side again. While I'm rewriting everything and distributing a negative 2 through, can you remind me, whenever you have an equation, what are the things that you can do when you have an equation? You can always do what on both sides? You can always add the same thing on both sides or subtract the same things on both sides. You can always multiply both sides by the same thing, right? Those are the types of things I can do. So I've removed the brackets by distributing a negative 2 through. Did I do that right? Yes? So I'm allowed to, at this point, look at this equation, and I can add or subtract or multiply or divide anything on both sides. Except I can't multiply both sides by 0. That's illegal. So watch what I'm going to do. I have no idea what this is, right? That's what I'm trying to figure out. But I know I'm supposed to have negative 4 of these. So I'm going to add 4 of them to this side. And I'm going to add 4 of them to this side. And this is like adding apples to apples. You add 4 apples, right, to what? This is 1 apple. You get 5 of them. Understand that? So what we get is, how many of these integrals? 5, you said? 5 of these integrals is equal to e to the 2x sine x. This went away over here, didn't it? And then we have plus 2e to the 2x cosine x. And that's all I have, right? That's it? And now I would like this to be just the integral, not with a 5. So why don't I just divide everything by 5, both sides of the equation? Is that okay? So I'm just going to have one of these is equal to this divided by 5. So I'm going to write 1/5 e to the 2x sine x. This divided by 5 plus 2/5 e to the 2x cosine x. And somehow, amazingly, we have integrated. We have actually found the antiderivative. Because look, we're saying the antiderivative of this is this, right? Now the only thing I'm missing here is the plus c. And that's because when you do it this way, when you have a problem that works this way, you never actually took an antiderivative, did you? Like you did it in your ultraviolet minus blue, the table, but other than that, like you never got an integral at the end that you finally integrated. It moved to the other side. So you never had that plus c pop out. So you just have to remember that all antiderivatives have to have some constant added. Do you see why we call it kind of like the rabbit out of the hat? Because you never really, like it appeared again, then you brought it over. So it's just weird, right? Should we check it? No, you don't want to check it? Why am I the only one who's eager to check these things? It works. We'll believe it works.
You get the same one. So you just stop when you get the same one?
You stop when you get the integral that you were looking for in terms of something that doesn't have an integral anymore. See, there's no more integrals over here. When you do the first step of integration by parts, your integral becomes ultraviolet minus integral voodoo, right? You have an integral still to work with. But we've somehow manipulated it to the point where the integral we're looking for is equal to something that no longer needs integration. So what you see, whenever you see this sort of combination where you've got a function that's never going to get better or it's going to cycle, then you kind of got to hope that it's going to reappear on the other side. All right, let's look at E. Now, I already gave you the hint, which is, I wish I wouldn't have put that up there, of what you're supposed to do. But let's just make sure we understand that we can't really do anything else first. That's just not E. This is not just like e to the root x, right? Antiderivative of e to something is itself. I mean, it is, but if this is a function of x, then that won't work, right? Because if you take derivative of that, it's itself, but then times derivative of what's up there, but that's not over there, is it? So, no go here. So you start thinking maybe integration by parts. But if you're going to do integration by parts, what are you going to choose for u? What are you going to choose for dv? Let's see.
DV is going to be dx.
You want to try dv as dx? And then this would be the whole thing up here? Yeah? We could do that? We could try this. Y'all want to try it?
It can't be the other way, right?
Well, let's just try it. Let's see what happens. Okay? This is right. And then coming down here, it's a little more complicated. This will be itself times derivative of what's up there. Like that, right? So derivative square root of x is 1 over 2 root x. Any questions on that? Okay, so let's do ultraviolet minus voodoo. Ultraviolet, x e to the root x minus integral voodoo is x times e to the root x times 1 over 2 root x, like that, dx. Do you agree? What else could we do with that? Is there a constant that we can pull out?
1/2.
1/2? Everyone see 2 down there? We can pull a constant out. I'll write e to the root x here. We have this x, right? And then we're dividing it by root x. What's x divided by root x?
X to the 1/2?
Which is just root x, right?
Oh, I'm sorry.
Is that right? Understand that? So we had this original integral, and when we did an integration by parts, we got this, and then a new integral, right? And look at this new integral. I think it actually looks more complicated than the first one, doesn't it? It's not only e to the root x, it now has a root x in it. And you might be thinking, okay, u sub, I can just do u sub. Let that be u. There's a derivative of it. No, that's not the derivative of it, right? 1 over 2 times this is a derivative. So this is going to make a basic U substitution. And it's not a very natural U substitution. By the way, that could be done. You could keep going, and it's just ugly, but it could be done. I'm going to make a U substitution to start the problem. It's not going to look very natural, but just watch how great things are going to become. I'm going to make this substitution. Now, I told you when you're doing basic U substitution, you're always supposed to be looking for something in its derivative, right? Right? But in this problem, if I'm letting U be root x, I don't see its derivative here. But there was one example I did show you where we made a substitution even though we didn't see its derivative, and it worked. So there's not like, when you make a U substitution, it doesn't always have to be that its derivative is there. If it is, then great. If it's not, then who knows? It might work, it might not. I know that's not what you want to hear, but it's just the reality of this material. So I'm going to make this substitution. The derivative of this is, let's go back around the tables. Josh, I know you know the derivative of this. I know everyone on this table knows the derivative of this, so I'm not going to ask you. So we'll move on. Lewis, derivative? 1/2, yep. 1/2. Where, you want the root on the bottom, right? Is that the way? And then dx, right? Agreed? And then if I try and make this substitution, I know that I can replace this right here with what? U. And then I have to replace dx. And I used to play a matching game, didn't I? I tried to match these things up on both sides. The problem is I can't match because this doesn't appear there, right? But I'm gonna try and isolate dx. I'm going to get this dx by itself. So if I'm going to get dx by itself, what do I have to multiply both sides by? 2 root x. So if I do that, I can replace dx up there in the problem, right? I can replace the dx with this. Jared, what do you think is wrong with that? I mean, not wrong, but what sort of trouble do you think I'm going to get in if I replace this root with u and the dx with this? Do you see what the problem is there, Jared? I'll write it out for you real quick. Is that? I'm going to have two variables in here, right? I'm going to have x and du mixed together. And I told you that the whole idea of rewriting the integral is to be able to get rid of the x and turn it into u, right? But that's not going to be a problem because what is root x?
U.
It's u. And so we got lucky. That root x is u. And so this actually becomes 2u du is dx. Right? And so really now when we rewrite this integral, we've got e to the u, that's this, and then dx is replaced with what? 2 du, or 2u du. I can pull the 2 out. I can move the u to the front. And now that's where I am, right? And then you look at that integral and you go, well, did that get any better? So let's go around. We'll open it up to this side of the room. Anybody over here? Tell me if you feel like you can do this, like if you can attack this, how would you attack it? That side of the room only. Just forget everything else here exists. All right? It's a brand new problem right there. There it is. I'll just put it in the corner here so we don't forget. We did make a substitution that u is root x. But ignore that. If that's the new problem, any ideas? Integration by parts. Why?
Because the u, the derivative of u is just 1.
That's right. Okay, so you have a polynomial. This is like x sitting in front of e to the 2x. And so you know if you use integration by parts, this, when you take the derivative, it'll drop down to a constant. Right? When you integrate this, it'll be itself. This is exactly like which problem? Well, it's not really up there, but it's kind of like A, isn't it? Where we had an x in front of sine. This is like an x in front of sine. This is going to switch back, right? I mean, it's not going to switch between sine and cosine, but it's not going to go away. Sine didn't go away either, but this one went down. Did y'all see that, everyone? So I'm going to do integration by parts on this. Good. If I do that, now watch what's going to happen when we do that. I'm supposed to choose what and what? U and dv. Uh-oh. I'm already using u. I can't use u again, because then you would represent two different things in the problem, right? Now I can use v, can't I? Because I haven't used v. So I can still choose a dv here. That still makes perfect sense. But I can't use u, so we'll use... Can't use x. X is already used. Z, K, right? Usually we'll use w. Now here's the thing. We like u, v, w. It's kind of like grouped together. Kind of like x, y, z. We like to use x, y, z together. We like u, v, w. Sometimes we like r, s, t. Those variables. So like if you're going to use s, then use r and t with it. It's just, this is just common stuff you'll see in mathematics. U, v, w. So I'm going to go to w now. I'm going to make a w substitution. So we can no longer use the cute little ultraviolet minus voodoo anymore, can we? So it's ultraviolet. I mean, it wouldn't make any sense. So it's more important for you to understand the formula, right? How to work with the table. This integral will become these two multiplied, right? Minus the integral of these two multiplied. What are we going to choose for w? U? For dv? E to the 2u du. All right, let's go. Where were we? Jared, I called on you. Let's see. We've done that table. James just answered, so it's... You volunteering? Or you have a question?
Where did that 2 come from?
Yeah, I was wondering that too.
You. Yeah.
It was in there. Remember we had that, we made substitution u was root x. Du was 1 over 2 root x dx, right? And when I solved for dx, I multiplied both sides by 2 root x du equals dx, right? Do you remember that was 2 root x, and then I replaced root x with u? Okay, so this became 2u du is dx, and then when we rewrote the integral, we replaced dx with 2u du. The 2 came out. Oh, so what? It's not a 2?
No.
Okay, sorry.
Yeah, I was wondering where that...
That was, no. Okay. I was thinking about the previous problem. That's what it was. Right, the previous problem was 2. Thank you.
saw that, right? I was like...
Thank you. You have to point those things out. And it's, you know what, it's actually a really good thing that you see that, because if you're sitting there and go, how the hell that happened, you either don't understand it or I made a mistake, right? So either way, you need to call it out. All right, that better? That better? Okay. I'm sitting here, I'm going, come on, Alexis. The 2, come on. What's that? Yeah, we'll fix it here. Thank you. Well, that's actually going to be nicer because the integration of that up is going to be easier, right? We don't have to scale it by a half. All right, well. All right, dw. We differentiate down is going to be du. And then v up, just e to the u. So this integral becomes 2. So this 2 right here is going to be passed through whatever I get now, right? Yes?
For v,
Uh-huh.
put 1 over u, e to u, or no?
No. If it was like 2u, which it's not, I don't know where you get that crazy idea from. If this were 2u, then you would have to scale by 1/2.
Yeah.
But you don't scale by the variable. It's the coefficient of the variable. Think about that just for a second. If you put 1 over u,
Because the U would fall off and you take the derivative.
if you take the derivative, you're going to have to do like a product rule now.
Yeah.
It's going to be nasty. It's not that. So, okay. We good? So this 2 is going to distribute through to whatever this becomes. That's going to become the formula ultraviolet minus voodoo, even though we're not using those letters. So we said across the top is kind of like the ultraviolet. So u times e to the u would be first. Minus integral, and then the diagonal, right? Which is just e to the u du. And is this an integral that we can handle?
Yes.
Absolutely. So this is a good thing. So this becomes 2, let's see, u e to the u minus, what's the antiderivative of this? E to the u. So just here, plus a constant, right? I'll do that at the end. In fact, I'll put it right here. I'll just put it right there. And now I'll pass the 2 through. 2u e to the u minus 2e to the u plus a constant. And I've had students ask me before, like, don't you have to multiply the 2 through, like, through the constant too? Like, shouldn't the constant have gone right here and the 2 multiplies through? It doesn't matter because 2 times a constant is still a constant. You don't know what that number is. It can be any number. So if I wrote 2c here, I wouldn't be wrong. But there's no reason to write 2c. And if I wrote negative c, it wouldn't be wrong either. It doesn't matter. Are we done? No, we have to go back to the original variable, which was x. So go root x. And so just replace all your u's with root x's. So this becomes 2 root x e to the root x minus 2e to the root x plus c. That should be the antiderivative. Questions? All right, I'd like to see if you can do one, all right, on your own. I mean, you can help each other out. But this is something that, remember from Cal 1, that if you had the natural log of x, right, the derivative of it was what? 1 over x. I wonder what its antiderivative is. So, that's true, right? And we usually use absolute value plus c. That's true. So this is the relationship here, but that's not what I'm asking. So please see if you can figure this out. Help each other out, okay? If y'all can figure this out, I'll allow you to write this on your formula sheet. Okay, it'll be something you can keep on your formula sheet. But y'all have to figure it out. All right, go ahead. Enjoy. My hint to you is that it involves the technique in this section, which is called integration by parts. You're welcome. You have a question? Mm-hmm. Plus C?
Oh, yeah.
You're asking me if that's correct?
That's what we got.
You check. When you get your answer, you take its derivative, you should get natural log x, right?
All right.
Works? You do product rule there?
Yeah.
Yep. Okay, good. That's it. That's correct.
It is?
Mm-hmm. So far. There's just one, right?
Oh yeah, true.
You got the right table there. Just do your ultraviolet minus voodoo. That's right. This is what's x times 1 over x.
1x squared.
Nope. One of them is on top, one of them is on the bottom.
Oh, it's 1.
1. Okay, so anti Okay, I'm just going to write the table up here. This is what you should have had. U is natural log x. dv should have been dx. Derivative of natural log x is 1 over x dx. V would then have to be the antiderivative, right, of 1, which is x, which is x. And then ultraviolet would be these two multiplied. I'll put the x in front of the natural log, minus integral. And then when you do v du, it's x times 1 over x dx. But x times 1 over x is just 1 dx. And the antiderivative of 1 is x. So x natural log x minus x, then plus a constant. That's it right there. You can check it. If you check it, you do a product rule on those, and things will start to go away, and you'll get natural log x. So you are free to write that down on your formulas. That's the only formula that I'm okay with you writing down, unless I tell you to write another one. All right. Be aware that on the test, right? If you come with your formula sheets, you can't have a bunch of your own stuff written all over them. It's not fair to anyone else. But that one you can have. All right. Well, we still have lots of time. Let's look at this last formula, or this last problem. Who has their book that has all the... Anyone have the book that still has all the formulas in the back? I think yours does? Yours does too. Okay, but you mind?
Don't make it smell like stain.
It doesn't smell... I still smell a little like skunk on my hands. It's not that bad, though, anymore. If you still have all these formula sheets... There is actually a formula on reference page 9. It's formula number 73. And there's 120 formulas in this book. Here's what the formula says. I'll write it down here for you. It's negative 1 over n sine of n minus 1, or sine to the n minus 1 of u. I better switch this over to x's here. Cosine x plus n minus 1 over n integral sine to the n minus 2 x dx. Let me just double check that. Negative 1 over n sine n minus 1 x cosine x plus n minus 1. That's it. Okay. So this is a formula in the book, and this is what we call a reduction formula. And let's try and appreciate what's happening here. Okay. Let's say I'm trying to find the antiderivative of sine cubed x dx. That will be very difficult to do, all right, with any technique that we have right now. Because, well, do you see the inherent problems with this? Like, what are you going to choose to let be your u and your dv? It's going to be a difficult choice. Now, you are allowed, you could split it up. You could write as sine squared x times sine x dx, and you could choose maybe that to be your u and this to be your dv. Okay? But it's going to be a mess. According to this formula, we don't have to do any of that. All we have to do is identify what n is, which for us would be what? 3, and then plug into this formula. So it'll be, for us, negative 1 over 3 sine raised to the n minus 1. So sine squared x cosine x plus n minus 1. 2 over n, which is 3, integral of sine to the n minus 2. So what's n minus 2? Sine x dx. Do you know the antiderivative of sine? Negative cosine, right? So this just becomes negative 1/3 sine squared x cosine x plus, actually it's going to be minus, won't it?
Yes.
Because I'll pull the negative out. Negative 2/3 cosine x plus c. And that would be the answer, wouldn't it? Yeah, if you don't have the formula, then you would have to do it more rigorously. The next section involves how we handle powers, basically trig integrals. Integrals that have trig functions in them. So we will do this the harder way next class. Or next time, well, next time we'll review, right? Well, we're not going to review for the whole day. We don't have enough time in this class for that. So we'll probably get into this next class, but it won't be on the test per se. Check my schedule. How far does the schedule say we go? Integration by parts. It says review, and we won't spend an hour 40 minutes reviewing. All right, this isn't Math 305 or anything like that. We don't spend 2 hours reviewing for a test in here. Sorry. But I wanted to give us a little bit of time. Well, it is more reviewing, but just not here. It's not happening in class. It's happening on your own. So, all right. So the usefulness of this formula would be that let's say that this power was, let's say, 7. Then things would change here, right? This would become 7, then this would become 6, and then this would become 6/7, and then this one would become 5. And then you're like, crap, well, I don't know how to do that. So what you do is say, but this part, this is your new universe, right? I do that formula again. And when I do that formula again, what integral will be popping out at the very end of it? Sine cubed. And then you do it again. But it's just fill in, right? Like you're never actually integrating anything. Look, no, it's reducing the power every time, isn't it? It's going from sine to the n down to the n minus 2. So if you do it one time, it's going to reduce the power by 2. If you do it a second time, it'll reduce the original one by 4 total. And you can do that, and you can take it all the way down to either sine or sine to the first power or sine squared. Those are the two different things that you could wind up with at the end. Sine to the first power is easy. Sine squared, well, we can do that next class. All right? That turns out to be easy also. So do you see sort of the value of this sort of formula to have it? Yes? Where does it come from? So that's what I'm going to show you where the formula comes from. All right? You have homework problem. You have, I think, at least one homework problem where you're asked to come up with a reduction formula. So this isn't totally out of the realm of feasible, reasonable questions to ask a student. Maybe not on a test, maybe as a bonus. But it's still something that you shouldn't look at that and be like, oh, man, no way. You know, this is doable, all right? I'll give you a big hint on how to start this. This is ultraviolet minus voodoo, believe it or not. That's ultraviolet minus voodoo. So if that's ultraviolet minus voodoo, then this has to be ultraviolet, right? Which means one of those is U, and one of those is V, right? So let's see here. What do you think? This is U, and this is dV. So you're choosing out of this one a U and a dV, right? Any ideas? Okay, U is sine to the n minus 1 of x. But I don't see that there. I mean, I do, but I'm trying to help everyone see it. Where is that here? Is x to the n the same as x to the n minus 1 times x to the first power? Is that the same thing? If you have the same base, what do you do to the exponents? You add them, right? Add these up. What happens when you do n minus 1 plus 1? You get n, right? So this is the same as this? What I want everyone to see here is that we could have rewritten this integral as sine to the n minus 1 of x times sine x dx. Couldn't we have? Now that's not a natural move to do that, but we could do it, couldn't we? If we do that, then you would choose your u to be sine to the n minus 1x. And that forces your dv to be what? Sine x dx. You follow that? And now let's go and write out everything that would happen now. So we're going to try and get to this formula at the end. Let's see if we can. What's the antiderivative of sine? Negative cosine x. And then very carefully here, what is the derivative of sine to a power? So I'll remind you, like if you had sine to the fourth x here, and I said take the derivative, first thing you would do is what? You bring the 4 out and then subtract 1 from the power, wouldn't you? And then you take derivative of the sine, which would give you cosine, right? So over here, we're going to drop what out front? N minus 1. And then it'll be sine to what power? Take 1 away, so n minus 2 of x, you see that? Times the derivative of sine, which is cosine, and then dx. I ran out of room. But do you see I'm starting to get pieces in here that it's kind of promising? Questions? All right. I want to leave that formula up here because I want to be able at the very end to go back and say, look, we got it, okay? So I'm going to say from here, what we have so far is ultraviolet minus voodoo. So let's do ultraviolet. It'll be this, right, times this. So that's negative sine to the n minus 1 x cosine x. That kind of looks like this, doesn't it? I have the negative. I have sine to the n minus 1x. I have cosine x. I just don't have 1 over n. It's okay. It's all right. At least I feel good about it, right? It looks kind of the same. Then, according to the formula, minus integral voodoo. So this times this. What are the constants? Are there any constants? Negative, right? Negative 1 and n minus 1. So I can pull out a negative n minus 1, can't I? I'm going to put that in front of the integral. When I pull the negative out, it's actually become what? Plus and n minus 1. Integral. And then all the other stuff. So what? Sine to the n minus 2x times cosine times cosine. Cosine squared? Times dx. The negative I already pulled out. This negative came with this and came out of the integral, and that's what made this a plus. Do y'all have any questions on this? We're not done, right? Does this look like this? Kind of, but I've got this cosine squared, this one doesn't, and so I don't know, now I'm starting to get a little concerned. Nope, nope. Watch. This equals negative sine to the n minus 1 x cosine x plus n minus 1 integral sine to the n minus 2x times, hey, what's another way you can rewrite cosine squared back from pre-cal? Actually, more complicated way. What was the Pythagorean identity? Sine squared x plus cosine squared x equals 1. So if I solve for cosine, I can rewrite the cosine squared x as 1 minus sine squared x, right? Now, the reason I'm doing that is because where I'm going with this has nothing but sines in it, right? So the only way I can get that cosine that was there to go away is to perhaps make it 1 minus sine squared x. And we still had dx. Do y'all see that? Now, this is multiplication, so this now has to pass through here and here, doesn't it? All right. Here it comes. It's about to happen. Okay, the original problem, right? Here was the original problem. Right? That was the original integral. We know right now that it is negative sine to the n minus 1 of x cosine x plus n minus 1 times the integral of this. So when you do this times 1, it's itself, right? So sine to the n minus 2 of x. And then when you do this times this, it's subtraction, right? Because you have positive times a negative. So it's minus, and what is sine to the n minus 2 of x times sine squared of x? Sine to the n. Right? Same base, sine x, add the exponents, n minus 2, add 2, and minus 2 plus 2 is just n, isn't it? So this is minus sine to the n x, and then dx. I haven't taken an antiderivative yet. Y'all okay with this? This is about to be pretty awesome. Does anyone see it yet?
Yes. Oh, you can separate the integral, right?
We can split this into two integrals, can't we?
You can add that to the other side.
And then this is the one over there, isn't it? And I can bring it over to that side, like the rabbit out of the hat. So watch. Integral sine to the n x dx equals negative sine to the n minus 1x cosine x plus n minus 1 integral sine to the n minus 2x dx minus n minus 1 integral sine to the nx dx. So what I've done here is I've used the fact that if you have an integral of something minus something, right? You can split it into two integrals, right? And this number right here is being multiplied, so it has to distribute to both, so that plus n minus 1 has to go in front of both. But since this one was positive, I just left it here like this, positive. This positive thing times that negative, right, would become a minus? Yeah? This integral is the same as this integral. How many of them do I have to add to both sides to make it go away over here? N minus 1 of them. Right? This is a number. This might be minus 10, might be minus 5. So I need to add that number. That's how many of those integrals I have to add to both sides, right? So I need to add n plus 1 of these integrals to both sides. No, minus 1. Sorry, minus 1. That would have been a disaster. I'm adding this. All right, we good? Okay, this is gone. I erased the thing we're trying to get to. Oh, well. How many of these guys, are over here? N of them, right? Because how many of these are there right here? One of them. How many of these? N minus 1. What's n minus 1 plus 1? Just n? So we have n of the integrals that we are interested in is equal to negative sine to the n minus 1x. I heard, oh, which makes, you had the little light bulb go off there? Yes? You see it? Plus n minus 1 integrals of sine to the n minus 2x dx. That's where we are now, because this was gone, right? And finally, divide by n. This is just a number, so just divide everything by n now. And when you do that, you get the reduction formula. Divide this by n, so I'll put negative 1 over n sine n minus 1x cosine x. Divide that by n, so n minus 1 over n integral sine n minus 2x dx. There it is. That's your reduction formula. Good? That's pretty cool, huh?
Is that formula on the one that you have on your, on the one that you just, yeah, on the formula sheet?
Like, is it up from your
It's not on those. These are the first, how many pages? 6. I think that's off page 8 or 9 on the formulas. No, and the reason is because I would never ask you to use this unless I gave it to you. But you need to know it exists. Okay, you need to know that there are formulas for things like this. And you need to know that these weren't like found in some cave by some alien being that came and gave us these formulas. Like, you know, we came up with these formulas on our own, right? All right, that's pretty awesome. I imagine that you could do the same thing for cosine. I imagine there's got to be a formula for cosine to the n then, right? And it probably works some formula. You could kind of get an idea of how they chose their u and their dv just by looking at it. All right, that's all I had for that. Now, so let me see here. I thought I'd bring up last semester's exam 1. I haven't made the exam, so I can't tell you how many, but this is what they took last semester. This was their exam 1. Let's see here. Hey, look at that. The bonus was to prove a reduction formula.
Did anyone do it?
Yes. 15 questions. So look, the first one, you know, has to do with inverse trig stuff. You know, just like evaluating. Like, find the value of this.
Oh, okay, use circle.
And then, you know, here's the derivatives. Take the derivatives. That's just making sure you understand derivatives of the different trig, inverse trig, hyperbolic trig. Proven identity. I think that was a homework problem.
Yeah, it was.
It was.
Yeah.
I think this entire test was homework problems. Or similar to. Here's a second derivative with some initial conditions. Actually, this was the one where you have to go back all the way to the original function, then you get a system of equations. So remember I came into class a couple of days ago and someone asked about, I think it was, don't tell me her name, Kirsten, right? That it? Kirsten had said, yeah, that was the one I had trouble with because we hadn't done one like that in class, and then I did it. So that's what that is. Now look, I'm not telling you this is what your exam's going to be. I'm just giving you a flavor of what I've asked before, okay? Here's an acceleration function. Go backwards. Find the position function and find the position function at pi. So this problem is a little easier because you're given information about position and velocity. but it involves trig stuff, so that makes it a little harder. And then the integration begins. How would you do that integration? Right there. Split it up into 2, and it's just powers of x, right? You rewrite root x over x, and then you rewrite. That's just power rule. Got to split it up. This one? Basic u sub. What would u be? 4 plus x cubed. Because the derivative of it's sitting right there, almost.
That's just
U sub, Alexis? What would u be? Square root of x. That's right. Because if you rewrote that integral, this is what the integral really looks like, right? And if you let u be root x, the derivative of it is 1 over 2 root x, and you almost have that. So you're just off by a constant. So that's basic u substitution. But if you start doing integration by parts on that, you're going to waste a lot of time. Which becomes one of the bigger issues on tests like this. Ooh, that's weird. Do you want to do that one? That's why I was showing you this. There's a few on here I thought we would do if we had time. Was that a homework problem?
No, but it was like to more powers.
To the third.
Yeah.
Split it up.
Yeah, yeah. That was one of you were like.
This is an integration by parts? Or no? What would you choose for your u if you're going to do integration by parts here? What would you choose for u? X, because it gets better when you differentiate it. But that means that you're going to need to be able to integrate everything else. So let me see. If I let u be x and dv be secant x tangent x dx, then it's going to be pretty clean. We'll just finish it. We'll at least write the line up there. Du would be dx. V would be antiderivative of secant x tangent x is just secant x. Just secant. Just secant, right? So derivative of secant x is secant x tangent x. And then you would have ultraviolet minus integral voodoo and then you need to know what the antiderivative of secant is. But it's on your formula sheet, and you have to have known that it was on your formula sheet. It was wrong page, derivatives, integrals. No, you were there. You were there. Reference page 6. It's formula number 14. Yeah, so this would be x secant x minus natural log absolute value of secant plus tangent x plus c. So this right here is formula 14 on there. So just always remember that you can always find the antiderivative of a single trig function. Like antiderivative of sine, we know that one. Antiderivative of cosine, we know. Antiderivative of tangent, just tangent, it's on there. Antiderivative of just secant, it's on there. Just cosecant, it's on there. Just cotangent, it's on there. Understand? All right.
Did this test on your review stuff?
No. Mm-mm. No, I prefer not to. I stopped posting tests a while back. I just kind of... Why don't you work on that one? give you some time. And substitution u is x squared, which doesn't seem very natural, the derivative of that is 2x dx, right? Which you don't have there. Well, yes, you do. So look, if you rewrite the integral as 2 times x squared times x times cosine x squared dx, that's the same thing, right? Just peeling the x cubed apart. Do you see,
Oh, yes, you do.
you actually have everything. 2x dx, right there, everything. That's du, right? And then this right here is what? U, and then this right here is what? U. So this integral becomes, all that other crap is just du, and then x squared is u, and then cosine x squared is cosine u, and then integration by parts on that.
Would you, so that's for W, that was about to,
Give us easy stuff.
Who has the book readily available right here? Let me see. That's insane. Insane in the membrane. Let's see here. Okay, well, you have to start by doing your homework, right? Oh, okay, here we go. So the reason why I was asking for the book, I know we're out of time, because people all freak out about this stuff, and then they get on the test and they take tests. They're like, man, that asshole, gave us all these problems, and, you know, I'm fine in class, and then his test, he makes them so hard and all this stuff. I'm going to write right now. This is page 316. This is number 29, which is an odd problem in this book. It is integral, and then it has numbers here, which I told you to ignore, right? Theta cubed cosine theta squared d theta. That's this problem right here, using thetas instead of x's. And in the problem here, they didn't give you the 2, so you had to account for that when you worked through it. The moral of the story is that this problem is not something that I'm going to pull out to make the hardest problem possible. If you do your homework, if you do the things that are asked, then you will have experienced this pleasure before you get to the test. If the first time you ever experience this problem is on the test, you probably are not going to get it. Right? So practice. Do your homework. I'm not going to try and pull out the hardest thing I can find, but I will ask you problems that I've asked you to look at. All right? Yes. What is the homework? Yeah, what's the homework for that section? Is it on here? No, you need to go up through 36. Yeah, I think you should try and do 1 through 36.
I think that's what it was.
Yeah, I think it's on the end of the notes. No, oh, here we go. Okay, 1 through 32. See, so look, there it is. You see, I gave that same assignment to my class last semester. Number 29 is in that assignment, right? Number 29 is in there. That's the problem I gave them. The only thing I did was change it from theta to x, and I gave them the 2 so that it worked even better here. Yeah. Okay, go.
Yeah, you just scale it to the other side, though. Like on this one, you
Yeah,
scale the other
yeah. This one you just have 1/2, but you would have to scale out. I didn't do roll.